Welcome back. So today we are going to state and start the proof of the main theorem of Galois theory. So in the last video I gave you a recap of whatever we have done so far about Galois theory, and I also gave you a few examples to motivate the main theorem of Galois theory. So I am going to state now and see how much of it I can prove today. And the proof, as I said, is a fairly easy one. So let K over F be a Galois extension, and I will only orally say here, but a Galois extension for us is always a finite extension. So we are also assuming that K over F is a finite extension, and in addition it is a Galois extension. So let K over F be a Galois extension and let G be the Galois group. So instead of writing GAL K over F, we are going to simply write G for this proof, for this theorem. So let G be the Galois group. Then the following statements hold. The first one is the statement that I indicated in my examples in the last video, which is a bijection between subgroups of G and intermediate fields of the extension. So more formally, there is an inclusion reversing bijective correspondence between, so I will simply write the sets here, subgroups of G. So this is a bijection, and intermediate fields of remember intermediate fields means it means a subfield L which contains F and is contained in K. So something like this, okay. So the right hand side is all L like this, which includes K and F. So intermediate fields of K over F. And it is given by, this is the point, so H goes to, H is a subgroup, you simply send it to K power H. We will show that, of course, it is easy, but we will expressly show that it is an intermediate field. On the other hand, if you take an intermediate field L, it is going to go to Galois K over L. We will see that it is a subgroup of G, right. So this is the exact maps in both directions, and it has the property that if H1 is contained in H2, that implies KH1 is contained in KH2. This is the inclusion reversing part of the statement. Similarly, if L1 contains L2, this implies Galois K over L1 is contained in Galois K over L2. Okay, this is all part of the statement. If L1 is a bigger field, its Galois group of K over L1 will be contained in Galois group of K over L2. And moreover, before I write to, moreover, this correspondence satisfies the following equalities. The order of H is the degree of the field extension K over KH, and the index of H is the degree of the bottom extension. So I am going to draw a picture in a minute, but that will clarify this. So K over the intermediate field given by H is H, the degree. K over H over the base field is the index of that H. This is confirmed in the examples that we did in the previous video. An intermediate field L of the extension is Galois over F if and only if Galois K over L, which is the corresponding subgroup to L, is a normal subgroup of G. Okay, it is a subgroup by this statement 1. L gives the subgroup Galois K over L. In general, it is merely a subgroup. If it is a normal subgroup, then L is a Galois extension of F. So maybe this is a bit confusing, so I'll just simply write an intermediate field L is Galois over F. Of course, it is an intermediate field of the extension. So if and only if Galois K over L is a normal subgroup of G. In this case, we have the Galois group of the Galois extension L over F is in fact isomorphic to G mod Galois group of K over L. G is Galois K over L is a normal subgroup of G by the first statement. So we can take the quotient group. Okay. So this is the statement of the main theorem. So I can't make the whole thing appear, but there are two parts. So K over F is any Galois extension with the Galois group G. Then we have two statements. First is that there is a bijection between subgroup of G and intermediate fields of K over F. So this tells me, by the way, why in all these cases there are no other intermediate fields in these examples, right? Because there are no other subgroups. So that is the statement. And in fact, we know more about this correspondence. The order of the group is the index degree here. The index of the group is the degree here. And this is normal if and only if this is, this is Galois if and only if this is normal. So all these are confirmed in these examples, but of course we have to prove this. Okay, so just to draw the picture, so you have K, KH and F. This is order H and this is index H. Okay, that is the statement here. Okay, so now let me start proving the theorem. So we will prove this. As I said, the proof is easy given everything that we have done. So we just have to carefully do all the steps. So proof is as follows. First we take, first we will prove 1. Okay, so let H be a subgroup of G. Then KH certainly is an intermediate field. This is a trivial statement, right? Of course, KH is contained in K because it is a subfield of K consisting of elements that are fixed by all of H. And F is contained in KH because every element of H is an F automorphism of K. Right? So every element of H is an F automorphism. That means every element of H fixes F pointwise. So F is in the fixed field. So KH is indeed an intermediate field. And now let's apply the, okay, so this is the first map. So I'm just saying that the map going from H to K power H is in fact a set map. You take a subgroup and you give an intermediate field. On the other hand, if you take an intermediate field, then this is something that we have observed several times in the past, but then we know that Galois K over L is a subgroup of Galois K over F, which is G. This is because if sigma is in Galois K over L, then sigma is an L automorphism of K. So sigma of alpha equals alpha for all alpha in L, and hence sigma of A is equal to A for all A in F, since F is contained in L, right? So here I am, okay, so maybe I'll just draw this here. K, L, F, that is given to you. So F is contained in L. So if an automorphism fixes L pointwise, it fixes F pointwise, and hence sigma belongs to Galois K over L. And it's a group, so hence Galois K over L is a subgroup of G. So this map is also well defined. So you take an intermediate field and you do get a subgroup. So we do have valid maps in both directions, right? So give me a subgroup, I map it to an intermediate field via taking the fixed field, which is an intermediate field as I argued here. On the other hand, if I take an intermediate field, I take its Galois group of K over that intermediate field, I do get a subgroup as I argued here. So we do have valid maps in both directions. To prove bijection, all you need to now is check is that we have identity when we compose either way. So let's start with H. Next we want to show that the maps are inverses of each other. So let's start with H and go to K power H. That is the map in the forward direction. Now you go back in the opposite direction. What do we get? By the map defined here, L goes to Galois K over L. So K over H, K power H goes to Galois K over K power H. But this is exactly equal to H. And this is, if you recall, in the last video I gave you a bunch of formulas that I recalled. Galois group of K over K power G is G for any automorphisms group G of K. Okay, so apply that to H to get this. So this comes from an earlier result, right? So this is okay. So that means you go from H to the fixed field and then come back, you do get H back. So on the other hand, let's take L. So now I am proving that you start with L, take the group and then combine, look at its fixed field. So L goes to Galois K over L. So this is the map from intermediate fields to subgroups. So L goes to Galois K over L. And now where does this go? This goes to K power Galois K over L, right? Because that's the map, H going to K power H. So Galois K over L goes to K power Galois K over L. And this is L, and this follows because K over L is Galois, right? K over L is Galois, so K power Galois K over L is L. So this is also recalled in that list of formulas that I wrote in the previous video. So K power Galois K over L is L. That means hence both the maps are inverses of each other. Right? So both the maps are inverses of each other. H going to K power H and then L going to Galois K over L are inverses of each other. Hence, so there is a bijection. Okay, so the bijection part is clear, right? Because we have two set maps between a set A and a set B. There is a map from A to B, there is a map from B to A, such that both compositions are identities, one on identity on A, the other is an identity on B. So A and B are bijections, A and B are bijective via those maps. So now, why is this inclusion reversing? Okay, so this is a triviality, so I will not spend too much time on this, but this is clear, right? If H1 is contained in H2, K power H1 contains K power H2. So why is this? So let's take something in K power H2. So let's say alpha is in K power H2. That means sigma of alpha equals alpha for all alpha in H2. But that means sigma of alpha equals alpha for all, so this is sigma in H2. So this must be true for every sigma in H1 because you give me a sigma in H1, it is in H1, so it is also in H2. So alpha has that property. That means alpha is in K power H2, H1. Okay, so that is okay. Okay, so essentially I am proving this. So now on the other hand, if suppose L1 is contained in L2, I claim that Galois K over L1 contains Galois K over L2. So why is this? So let's take sigma in Galois K over L2. Right, so I want to show that it is contained in Galois K over L1. This means sigma is an automorphism of K such that sigma restricted to L2 is identity, right? So let me write 1. That is the meaning of an L2 automorphism of K. So sigma is a K automorphism of K which fixes 1, L2, every element of L2. But this means sigma restricted to L1 is also identity because L1 is contained in L2. So sigma of alpha equals alpha for every alpha in L2. That means sigma of alpha equal to alpha for every alpha in L1. This means sigma is in Galois K over L1 also. So you took something here and showed that it is in this. So it is an inclusion reversing bijection. So far so good. So what we have shown is there is a bijection, it reverses inclusions. Now let's prove the last part. This is also trivial. Let H be a subgroup of G. Then the index of K over K power H is equal to order of H. I mean, this is a fact from before. Or result, let's say we proved this result from before, right? This is recalled for you earlier. So this is the first statement there, right? So this is the first statement. So you have K, K power H and H, F. So this is exactly the order of H. So that is okay. But now we do know certain things. So order of G, because of the product rule for group theory, in the group theory that you have learned in when you learn group theory. So order of a group, finite group G is equal to order of the subgroup H times the index of the subgroup. On the other hand, we also know K over K, the degree of K over F is equal to the degree of K over KH times degree of KH over F. So this is equal to this times this. These are both facts that we have studied in their respective courses. This is from group theory, this is from field theory. Now what we know is that this is equal to this because it's a Galois extension. This is because K over F is Galois, right? And this is equal to this. This is the fact that we just recalled, earlier fact, right? So then these two better be equal. So this implies okay. So G colon H is KH colon F, right? So this is G colon H, KHF. So this is exactly the last statement of part 1. So this is actually a consequence of this. So this, once you prove this, this follows. So this is a nice, even the statement 1 is a nice structure theorem for Galois extensions. Every time you have a Galois extension, you have a complete knowledge of all the subgroup, all the intermediate fields of the extension, just using what we know about Galois group and its subgroups. And we further know about the degrees of the various field extensions. Okay, so before we prove number 2, let me just go back to the examples that we looked at in detail. So here you have subgroups of order 2, hence these are order 2. These subgroups also have index 2, so these are also degrees 2. And in this example, H prime is a subgroup of order 3. So K colon K power H prime is order 3, degree 3. H1, H2, H3 are subgroups of order 2, right? Hence, K is degree 2 over the corresponding fixed fields. And hence, the index of H prime is 2, so this is 2. Index of H1, H2, H3 are all 3, so these are all 3s, okay? So, and of course, there is no relationship between inclusion relationship between H primes and H1. So there is no inclusion relations between these 4 subfields. Okay, so these 4 intermediate fields. Similarly, there is no, there is no inclusion relation between these L1, L2, L3. However, in the finite field case, there would be, I didn't analyze this fully because it's going to be messy to draw the tree here, but there will be inclusions of the subgroups here, and hence there will be inclusions of the intermediate fields here, and inclusion reversing things here. So let me actually stop the video here because I don't want to go fast over the second part and it will take me more than 10 minutes. So what I want to do is to just remark that this bijection fails when K over F is not Galois. So let me quickly give you a simple example and then we'll stop this video. Okay, so what is the reason that this fails? This fails. What is an example that this fails? Let's take K to be Q adjoint cube root of 2 and F to be Q. So in this case, this is not Galois, as we know very well, as we have several times mentioned this. And what is the Galois group here? It's just the identity. Okay, so there is exactly one subgroup of G, but there are 2 intermediate fields. Namely F and K. They are not different, they are distinct, right? F and K are distinct fields. This is a degree 3 extension, they are distinct fields. So there are 2 intermediate fields. Here there are 2 elements in this set. In this set there is only 1. So the bijection fails. So the assumption that K over F is Galois is extremely important. Okay. So, and you might, it's a good exercise for you to go back to the proof and identify all the points where we have used Galois property, right? So K over L is Galois because K over F is Galois, and this is not just the only place. There are several places where bijection will require the fact that it is a Galois extension. So let me stop this video here. I will continue with the proof and prove the second part in the next video. Thank you.